In this online lecture, we're going to discuss the third aspect of NMR, and that is very important. There is a relationship between the area under a peak and the number of hydrogens responsible for that peak. Let's make sense of this here. Let's look at a sample right here. Let's look at this molecule. We stick him in the NMR. And remember our first aspect here, we would expect to see a peak for this A-type hydrogen and a peak for this B-type hydrogen, which means his NMR spectrum would look something like this. We would see two signals, and we also learned the second aspect of NMR, that the A hydrogen would be more shifted than the B hydrogen. However, now let's look at the third aspect here. Let's say you could somehow calculate the area that's underneath this A peak. And let's say somehow you can calculate the area under this B peak. The NMR machine can actually do this. If you've taken calculus, you remember that the area under a curve of a given function can be calculated by taking the integral of that function across a given interval. If you haven't taken calculus, who cares? There's a way to calculate the area, that's good enough. What I want to show you here is a very important relationship. If you took the area of A and divided it by the area of B, you would get a certain value, and that value would happen to be equal to 2 to 3. And here's the important relationship. 2 to 3 actually happens to be the ratio of A hydrogens to B hydrogens in our sample. Notice, look at our molecule here. There are 2 A hydrogens for every 3 B hydrogens. This is not a coincidence. So that is our third aspect. There is a relationship to the areas under a peak in the NMR to the hydrogens giving rise to that peak. However, let me show you another way to interpret this. Typically, in an NMR spectrum, we not only see the peaks, but for our given sample molecule here, if we put him in the NMR, we would also see a line like this. What the NMR machine is doing for us here is it's converting the area under the peak to the length of a vertical line. Meaning, look at the A peak first. Whatever area he is proportional to the length of this line. And the area under the B peak is proportional to the length of this line. If you were to take these two vertical lengths right here and compare them to each other, you'll notice that the A length is 2 to his 3. This means if we have this line in our NMR spectrum, we can take out a ruler, measure their relative lengths, and that could give us a particular ratio. And again, that ratio would match the ratio of hydrogens in our sample. Now, you might be wondering, who cares? Well, what you're going to see a bit later on is how this is going to help us determine structure. This is actually a big deal. All I care about now is that you understand this relationship. We'll learn how to use it later. So that is our third aspect of NMR. That is, remember, there is a relationship between the area under a peak and the number of hydrogens responsible for that peak.